Hi everyone, I'm Jihwan Oh from KAIST. Today, I'm going to introduce filtered direct preference optimization, which is published in EMNLP 2024. This paper covers the importance of data quality and the filtering process in direct preference optimization. First, I want you to give a brief background of preference optimization. So, preference optimization is the final stage of LLM training. As you can see in the bar chart, as colored in blue, the first training step is pre-training. Pre-training refers to training a large language model on a massive unlabeled text corpus in an unsupervised manner. Supervised fine-tuning, SFT, is the subsequent process of taking a pre-trained model and refining it on a labeled dataset with a specific task or instruction-based supervision. This step tailors the model's behavior to better handle prompts or desired outputs. Direct preference optimization, DPO, is an alignment approach where the model parameters are adjusted to increase the generation probability of chosen responses while reducing that of rejected responses. The example of chosen and rejected data is shown in the middle figure. When using GPT, when you enter the prompt, you may be asked which of the two answers you prefer, as shown in the picture. Using these chosen and rejected datasets, we can make LLM more aligned with humans. So this is the concept of preference optimization. So reinforcement learning from human feedback is the one of ways to optimize language models using human preference data. As you can see in the figure in the middle, we train the reward model using maximum likelihood estimation. The reward model outputs float values that represent the preference of humans. High reward means high preference and low reward means low preference. Consequently, the goal of model is to calculate how much data is preferred on a human basis. After training the reward model, it's time to train the language model using reinforcement learning. The trained reward model evaluates the current language model policy by assigning rewards to generate responses. Using proximal policy optimization, PPO, or similar reinforcement learning algorithms, the LM policy is updated to generate higher quality responses. In summary, there are two steps. The first step is to train the reward model using SFT. And the second step is to training policy model using reinforcement learning. Again, these are the stages of RLHF in writing. The first step is supervised fine-tuning. It refines pre-trained LLM for downstream tasks such as instruction following or summarization. But if we use an instructed tuned model, we don't need SFT. The second step is reward modeling. It constructs a reward model to capture human preferences. Equation 1 shows the reward objective. The reward model is optimized to give a high score to the chosen response and the low score to the rejected response. And the last step is reinforcement learning fine-tuning. It optimizes fine-tuned language model using reward model. As you can see in equation 2, the goal is to enhance language model by maximizing the reward while maintaining closeness to the reference language model. So this is the basic process of preference optimization, especially RLHF. However, it has limitations that we need to train two models, the reward model and the language model. So instead of RLHF, direct preference optimization reformulates the reward modeling and reinforcement learning fine-tuning paces to a single optimization problem. While DPO essentially follows the same loss function under the Bradley-Terry model in RLHF, DPO is a reward-free model approach that aligns the SFT model directly with the preference data. This figure shows the direct preference optimization. We can directly fine-tune the language model using preference data without a reward model. To sum up the background about preference optimization, this table shows the comparison between conventional RLHF and TPO. RLHF first trained a separate reward model using human feedback and then applies reinforcement learning to optimize policy based on the reward. This method offers greater flexibility for handling complex preferences, but involves a complex pipeline, instability risks, and reward hacking where the model exploits loopholes in the reward function. On the other hand, DPO skips the separate reward model. It directly increases the likelihood of chosen responses and decreases that of rejected responses. However, it's less flexible, less established, and heavily depends on high-quality preference data. So now let's move on to the motivation of this paper. The keyword of this paper is the quality of preference dataset. Dataset quality is important in any training process, but its impact on the RLHF or DPO framework hasn't been widely studied. Preference dataset quality strongly affects DPO-optimized language models, but has less impact on standard RLHF models. For example here, Figure A shows the performance variation of RLHF and DPO. The blue line shows the model performance training with a high-quality dataset. And orange line shows the model performance training with a mixed quality dataset. RLHF is robust to dataset performance, but DPO is sensitive. The authors propose filter DPO, simply called FDPO, which improves dataset quality by using a reward model to filter out raw quality data. As shown in Figure B, the blue one shows the model's DPO performance using high-quality datasets, and the orange one shows the DPO performance using mixed-quality datasets. FDPO using data filtering shows better performance even on mixed-quality datasets. Now let's move on to the methodology. This is the pseudocode of filtered DPO. It may look complicated, but it's simple. First of all, we accept the language model and reward model as written in the first and second lines. And the remaining part is about DPO fine-tuning with filtering. Before DPO training, we initialize training set D preference. The preference data is triplet including prompt, chosen response, and rejected response. If you see the line 8, we use the pre-trained reward model to compare the chosen response and generate a response using the language model. Here, the language model has not been trained yet. So the key point here is that if the chosen response is worse than the language model, it doesn't need to train the model. So if so, like line 8, we discard the preference triplet from the original training set. And after filtering, we're training using DPO with the filtered dataset. It's the end of the algorithm. The highlight is that we need a data filtering process using a pre-trained reward model before DPO training. And the author said the motivation of this study stems from the observation that the quality of data in DPO significantly affects the performance of the resulting language model. More specifically, upon differentiating the objective function of DPO in equation 3, we obtain the gradient of DPO loss like equation 4. Equation 4 highlights that DPO, while adaptively adjusting sample weights, inherently aims to increase the generation probability for the chosen response and decrease it for the rejected response. This approach can lead to two types of problems. First, high quality responses are labeled as rejected. And second, low quality responses are labeled as chosen. In the first case, the author said it doesn't affect that much. This means that the capability of language models could remain robust. Because extensive diverse potential responses will ensure that surpassing some responses does not substantially reduce the language model's capacity to generate other high-quality alternatives. However, in the second case, if lower quality responses are labeled as chosen, it's critical to language models because an increase in of probability of low quality responses inevitably decreases the share of high quality responses. They also provide a theoretical analysis of this statement. So if you are interested, please refer to the appendix in this paper. Now let's move on to the experiment. First, pre-trained models. They train the various size of Pythia to obtain language models and reward models. For evaluation, they use the gold reward model, Diverta Large. They also use GPT-4o model as an alternative to human evaluation. Now, datasets. They experiment with their filtered DPO on two datasets. The first one is Alpaca Farm. It's designed to help models generate responses that both helpful and harmless. It aims to ensure that models provide useful information while avoiding harmful or unsafe content. This dataset includes 44,000 training samples and 2.3 thousand test samples. And the second one is Alpaca Farm. It's credited for collecting diverse instruction response pairs and evaluating the quality of generated responses. This dataset include 20K training samples and 2K test samples. These two datasets are often used in research focused on model alignment and safety, such as RLHF or DPO. They also conducted synthetic datasets. The low-quality dataset is made conventionally. A language model of Pythia generates two responses. Then, these responses were evaluated by the gold reward model with the higher scoring response designated as chosen and the other as rejected. The higher quality dataset is made by best of n sampling. Pythia generates 16 responses, and these responses are also evaluated by the gold reward model, and the highest scoring responses was selected as chosen, with one randomly selected from the remaining 15 responses labeled as rejected. And lastly, a mixed quality dataset is made by mixing the low quality and high quality dataset in 50-50 ratio. Now let's see the result. First of all, see figure 3 as shown in the left top. It displays the impact of reward model size. Smaller reward model relative to the language model size yield better performance. The author said that this contrasts with other studies and highlights an area for further detailed analysis. And as you can see in the middle on the top, figure 4 indicates that reducing randomness did not yield improvements, and in some cases, it led to worse performance. This result shows the randomness of output is not significantly important. And figure 5, right on the top, shows margin and the performance. Here, margin means the minimum standard of discarding data in the sampling process. If the reward of the original language model's response is higher than the sum of the chosen response and margin, it should be discarded. The result shows that larger margins generally lead to a decrease in performance, with a best result achieved when low margin is applied. This suggests that setting a margin is not necessary for enhancing FDPO's performance. And lastly, Table 1 shows the gold reward model and GPT evaluation. Here, the gold reward model is just a preference score evaluated by the gold reward model. And the GPT evaluation metric is the win rate between the tested and the output. As you can see in the table, DPO outperformed the baseline in both evaluation metrics. Especially, GPT-4 evaluation results suggest that FDPO is not just optimizing for the reward model, but it is also learning to generate higher quality responses from a human evaluation perspective. Now let's move on to the conclusion. First, this study explores how the quality of preference dataset impacts language models optimized using DPO, especially when compared with RLHF method. Second, they found that the quality of chosen responses significantly influences DPO performance. And third, to address this, they proposed filter DPO, which uses a real model to identify and discard lower quality data. And also, experiments demonstrate that FDPO improved DPO's performance by effectively handling datasets with quality discrepancies. And here are also limitations. First, the method requires a real model, even if they didn't use reinforcement learning. It might be a drawback as it increased the complexity and computational time of the method. And second, their approach does not account for rejected responses, which could further enhance performance if considered. And lastly, they use small LLMs and comparisons with um, only live DPO. Yep, and this is the end of presentation. Thank you for listening.